Okay, we're working on chapter 6, part 2. So the part 2 I have right now is actually supposed to be part 3. So this is going to be part 2, and I'm going to start right here. So when we left off from part 1, we're talking about the rigidity of a bond. So we're told here that when you encounter a molecule that has single bonds, like we see right here in this Lewis structure, single bonds tend to have free rotation around those single bonds. Now, it's kind of difficult for me to show it right here, but in the picture, we're showing that you see where the chlorine is on the bottom on either side of this molecule? Because this single bond here, or the sigma bond, allows for free rotation, it is common for us to see the same chlorine surrounding atom up here, and then maybe later on back here, because the bond is constantly rotating. So the chlorine will move around. And in the chlorine kind of rotating around that central atom, the carbon right here, it doesn't really change the identity of the molecule. The molecule is still seen as this molecule up here. Once again, the chlorine can be here in one instant. The next instant, you might see it up here where the hydrogen is, and they'll switch positions. And then it might also be up here, right? This happens because the single bond is constantly rotating. And if it's rotating, the atoms can kind of shift around. So that's the feature that we are able to understand from the valence bond theory. Lewis said nothing about free rotation around the central atom, right? Or free rotation in the single bond. But the valence bond theory tells us that. Anyway, because of that behavior is observed in single bonds. But when you have a double bond, we cannot have free rotation. What prevents the free rotation, as we mentioned before? That will be done by, let me bring the red color here. The second bond, the pi bond that bridges over the sigma bond, this doesn't allow for free rotation. When the bond here tries to go around and rotate, this pi bond is rigid and it prevents the rotation. So why is all of this information important? Scientists observe that these two molecules here, they're called isomers. Now, in the world of chemistry or science period, iso usually means same. Something about the things that are being referred to as iso is the same. Remember, you have isotope, you have isotonic concentration in solution. Iso usually just means the same. There's something about these chemicals that's the same. If you look at these chemicals here, they both have 2 carbons, right? 2 carbons. They both have 2 hydrogens, and they have 2 chlorines. So we can say the molecular formula is the same. Remember, the molecular formula tells you what elements are present and how much of each of those elements we have. So for both molecules, we have 2 carbons, 2 hydrogens, and 2 chlorines, right? But what makes them different? There's something about them that makes them different to where we are not calling them the same molecule. If you look right here, it is the location or the position of the chlorine. In the molecule on the left, the chlorines are on the same side of the the double bond sign, right? It looks like an equal, but it's actually a double bond. So we have the chlorines on the same side. Instead of having to describe it that way using a lot of words, that's mentally fatiguing, they call molecules like this cis molecules, where you have the groups of interest on the same side of the double bond, okay? When the groups that we are interested in are on opposite sides, you can see one here is below, one is on above, we call this a trans molecule. So trans being opposite of the double bond, and then cis being on the same side of the double bond. But don't forget, apart from that difference, this molecule essentially has the same molecular formula, right? Same elements in same amounts. So what allows these molecules to be completely different all the time is because the double bond does not allow free rotation. If this bond here between the carbons with a single bond, it will essentially be the same molecule. But since it's a double bond, the chlorine is essentially stuck next to the other chlorine, making this molecule here, cis 1,2-dichloroethene, a different molecule from the trans 1,2-dichloroethene. Remember, the only part of the name that makes this different is the cis and the trans, telling you the groups of interest, the two chlorines on the same side in one molecule, the cis molecule, opposite side in the trans molecule. Okay. So when you take organic chemistry, if you happen to take that class later on in life, you'll be learning more about different types of isomers that exist in organic chemistry. These are molecules that have the same molecular formula, but different structural formulas. The atoms occupy different spaces, or the bonds are slightly different. So we're not diving into that. We're just saying that exists. And the reason why that exists is because the double bond does not allow for these groups to freely rotate. Okay, so they're completely different bonds, different molecules. For us to go from the left molecule to the right molecule, you have to actually break the double bond and then rotate the chlorine upwards and then reform the double bond. That means that requires a chemical reaction to go from the left to the right. Okay, once again, proving to us these are two different molecules. Okay, so after we saw all that, in the chapter, we're now looking at sp hybridization. In sp hybridization, we're told here, when two carbons are forming a triple bond like that, around this central carbon, this is essentially sp hybridized. How do we know that? If you look at the number of electron groups here, we essentially have one electron group, a second electron group here. The one on the left could be bonded to a hydrogen. The one on the right is bonded to a carbon, right? Remember, the bonds grouped together count as an electron group. So this would be one electron group. The single bond by itself on the left side will be the other electron group. So together we have two electron groups. When you have a central atom, which is carbon, surrounded by two electron groups, the arrangement we have around the central atom tends to be a linear geometry. So the groups will arrange themselves so they're in a linear fashion with a bond angle of 180 degrees, okay? So when it comes to the hybridization, remember you're going in order of S, 3 Ps, and then 2 Ds. You're selecting the letters and you're selecting the number of letters to match the number of electron groups. Since we only need 2 electron groups, we're only going to be using the first 2 letters here. So the carbon in the center, the central carbon, uses sp hybridization to bond. Okay, so how do we get the sp hybridization? This is showing you the carbon right here. And so I wrote on this stuff before. We see the carbon right here, and we're seeing the orbitals in the right order. So remember, Aufbau says you want to make sure you use up the lower energy orbital first before you go to the higher one, right? So carbon contains all of these orbitals here. 1 in the 2s sublevel, 3 in the 2p sublevel. But for this bonding style, carbon will use the s and 1 of the 3 p's. So over here, they're having you essentially mix the s and the p, right? So let me go ahead and create a whole new box on the side. Okay, there it is. Okay, so we'll deal with acetylene or ethene right here. So this right here. We have a carbon that has a triple bond and a single bond right here. So my focus is only on the carbon on the left. We're trying to describe the bonding here, right? Based on the number of electron groups here, we need 2 electron groups. So there's a group here and a group here, like I mentioned before. Since we have 2 electron groups, from the hybridization letters, we're only going to be using the first 2. And these first 2 are S and P. So we're saying carbon uses sp hybridized orbitals for its sigma, it's sigma bonds, okay? Like we saw earlier, how do we show this for carbon? We said once again, the configuration for carbon is going to be helium, and then we have the 2s that's going to be just one box, right? And the 2p level that usually has 3 boxes. Okay. For carbon, we of course have 2s2 and then 2p2. Okay. So what we're doing here is now when they show this here, they make it very easy because all they're saying is, well, just go ahead and mix one of the two S's, or the two S orbitals, right? You only have one 2s orbital. So essentially what they're showing here is take the 2s orbital and mix it with the first 2p orbital. But the story isn't that simple. Okay, and let me show you why. So when I'm showing you this play out in an actual molecule, the 2s orbital or sublevel has 2 electrons. The 2p also has 2 electrons. You have an up and up here. Now you can see from the bonding here on carbon, right? Carbon has to form 2 total sigma bonds. It has to form a sigma bond with the hydrogen on the left. It has to form 1 sigma bond with the carbon on the right. Then it has to form 2 pi bonds. So in your mixing of the orbitals, you have to select the right orbitals to mix so that this bonding is possible, okay? So we're going to do some trial and error here to pick the right orbital. If we go by what the book was suggesting, right, just take the S and add it to the first P, it may or may not work out. Let's try it out. So I'm going to use a different color for this part here. Say we try to mix the S with the first P, okay? If we mix those, we're essentially hybridizing these to create hybrid orbitals. The hybrid orbitals are degenerate. They're stuck side by side. They now have new names. Their names are the hybrid names. So SP and SP. And then we have two unhybridized p orbitals that did not get hybridized right here. Based on what we have here, one is this, the second one is that. So I'm going to put 1 electron here. This would be empty. Now I have 3 electrons to distribute in the hybrid orbitals, right? Those will be up, up, down. Now, does this configuration match the bonding here? Let's see. We're saying this is happening with carbon, right? So our central carbon now only has room for 2 bonds. Based on what I have here, a bond can happen here, and a bond can happen here, but no bond can happen here because remember, in this chapter or in this section, for you to have a covalent bond according to the valence bond theory, you have to have unpaired electrons available. Then the other element brings in its unpaired electrons. These electrons essentially form whenever the orbitals overlap. So we only have bonding space available for 2 bonds. If I draw the bonding structure around this carbon, it will look like this. The carbon will have a single bond from here, the sigma bond, then an additional bond from here, the pi bond. So this here will form a sigma bond, this here will form a pi bond, and then what does this become? This ends up being a lone pair. This doesn't match what we have up here. So we can go back and say this configuration will not work. We have to go back, okay? So the way that the author in the textbook shows it, he kind of oversimplifies it. So I'm going to show you how this really plays out. The way this plays out here is a little bit more complex. You have to select the right P. You're going to select only one P, but the P you select has to be right so that in the end, it matches the Lewis structure, right? So going back here once again, we're going to start with 2s2. We have 1 sublevel with 1 orbital with 2 electrons. Then we have 2p2. We have a sublevel with 3 orbitals. And then you have electrons like this. Since the first one did not work, the second one won't work either. So I'm going to go for the third P. I'm going to select the whole s orbital, and then I'll go with the third p orbital, the empty one. So why did I select that? That allows me to actually increase the bonding capacity for carbon, and you see how it plays out. So when the s overlaps, when the s gets mixed with the third p orbital, we end up with, once again, 2 boxes. We mixed 2 boxes and we got 2 boxes here. And these 2 boxes are each named the hybrid orbital, sp, sp. But this time I have 2 electrons to distribute here, right? They go up, up according to Hund's rule. And then the remaining unhybridized The remaining unhybridized p orbitals end up here. And this will each be called the p orbital. These will have unpaired electrons here. Why is it important to have these unpaired electrons here? Because if you're planning on making pi bonds, only the unhybridized p orbitals can be used, are used for pi bonds. And remember, pi bonds are essentially any second or third bond. Okay. So once again, the reason why I didn't want to go with that one here, because this kind of implies whenever you encounter the first p orbital, that's the correct one to pick. That's not necessarily the case. You have to kind of, by trial and error, select the one that gives you the configuration that matches the Lewis structure. So over here, let's see how it plays out. Now our carbon has got 4 spots to bond, right? These first 2 in the sp orbitals, these would be used for sigma bonds. Let's see if that makes sense. In our carbon right here, these are our sigma bonds. The sigma bond there and a sigma bond here. So that makes sense. Yes, carbon will use the first 2 hybrid orbitals for sigma bonds. And then we can see right here in the red, I haven't changed that, the carbon has got a second and a third bond with the neighboring carbon. So here's where you have the second and the third bond, and these are both pi bonds, okay? So once again, the way you hybridize and the way you mix the orbitals to create the hybrid bonding has to be consistent with your Lewis structure. So I like to have that close by so I can confirm it. So the carbon will form its first bond with hydrogen right here. The hydrogen will bring in its 1 electron to form a bond here. And so we'll have our first bond between carbon and hydrogen right here, right? Like that. And then the carbon will form 3 bonds with the neighboring carbon. So the neighboring carbon right here. The first bond forms right here. The second bond forms right here. The third bond forms right here. And this essentially explains the triple bond, right? Well, the first bond being the one that's sigma, the second and the third one being pi bonds. Any questions about that? And so here they kind of, okay, sounds good. Here they kind of cover how the sp hybrid orbital is made. So remember, the orbital diagrams are simplified versions of the actual orbitals, but here they're showing you the actual orbitals mixing, right? You take one s orbital and then mix it with the 1 p orbital, and you end up getting 2 equivalent hybrid orbitals which overlap to give you this. This is just a detailed explanation of how we get the hybrid orbitals, right? Now over here, I've kind of written all over this. The Lewis structure I showed you guys earlier, that's shown over here. Okay. And it's kind of giving you the play by play. So once again, carbon uses, I think I used blue earlier, right? Carbon uses the hybrid orbital. So the hydrogen is using S, right? That's hydrogen. Carbon is using the hybrid orbital, which would be sp, to form the sigma bond with hydrogen. And then it uses sp to form all the first bonds of the sigma bond. So that's right here, right? It forms 2 sigma bonds total. Then it goes back and bonds the second time with the carbon. And then it goes back and bonds the third time with the carbon. The second and third bonds are all called pi bonds. And for that one, it uses the unhybridized p orbitals, right? So over here, we see it play by play, or at least we see the details here. Once again, the carbon uses the sp orbital, that's the purple one that we're seeing right here, the sp orbital, right, to form the first bond, the sigma bond. Sigma bond, the carbon uses sp orbital. Same thing with the other carbon, sp orbital, to form the sigma bond. The hydrogen uses the s orbital, actually the 1 s orbital to be specific. And then the carbon goes back and uses the 2p unhybridized orbitals to form the pi bonds, right? Oh, here they just call them p. Okay, that works. P works too, from the pi bonds. Anyway, so let's see. Oh, the next part here, we're looking at getting to the valence bond model. So I do not try to draw this one here because it is very complex. For this one, when it comes to your homework, the most you're going to be doing is labeling, right? We're not going to try to draw that part because it gets very complex. It's hard to really draw the pi bonds as the unhybridized p orbitals kind of bridge over, right? I struggle to draw that part. The next part I want to show you guys here is I'm going to draw this underneath. This is going to be ASF5. Okay. So for ASF5, I'm going to draw here, add a page, and then draw this right here. So we're working on ASF5. So to make it easier for me right here, we're doing the shorthand configuration. And the configuration shows us here that we're dealing with the 4S, 4P, and then 4D level. So, okay, AS is in the same group as the ammonia group. Okay. So what we have here is a shorthand. We have, we're dealing with 4S2, and then 4P3. When you draw ASF5, AS in the formula, let me write this right here. AS, we have one AS. It's in group 5, right? So that's going to be 5. And then we have 5 fluorines in group 7. So we end up with 35. So we're working with 40 electrons, right? So from here, our noble gas element is going to be AR. I may as well just add that here too, AR. From here, we're going to draw our Lewis structure. So we have that as an anchor to keep us on track, to keep me on track. I have AS in the center here. And then we have 40 electrons to distribute around AS. Surrounding the AS is 5 Fs. So we have the axial Fs. We have the equatorial Fs. We have 5 Fs to put around the AS. We're going to be using 2 electrons each time to draw a single bond. So we got up, down, left, right, top right, and bottom right. I just used 10 electrons, right? I made 5 bonds, 2 electrons each. I should be left with 30 electrons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So I just did 6 times 5 minus 30, so I am out of electrons, okay? I'm trying to conserve space, so I just drew my Lewis structure to the right. Oh, I keep forgetting about this feature. This is a fun feature. Okay, so from right here, I do have my condensed structure. Let me write it again. So I have AR 4S2 4P3. Okay. This is going to be in brackets. I need to have my hybridization. So my hybridization here, as I mentioned before, is based on me selecting which orbitals I have to mix up. Now, the menu that I have to work with is 1s orbital, 3 p's, and 2 d's. So I'm going to select the number of letters I need based on the number of electron groups I have. Since I have 1, 2, 3, 4, 5 electron groups, I have to select the first 5 letters. So I'm going to go 1, 2, 3, 4, 5, right? So my hybridization, I'm going to consolidate the letters. I use 1s, I use 3 of the p's, and I use 1d. And this goes with 5 electron groups, okay? So in my hybridization, I have to make sure I mix the 1s orbital, 3p orbitals, and 1d. Okay, I need the condensed configuration right here, the shorthand configuration to draw my orbital diagram. And in my orbital diagram, I'll put the 4s on the bottom with my 2 electrons. The 4s sublevel tends to have 1 orbital, 1 box. What's next? 4p sublevel. I have 3 electrons. The 4p sublevel tends to have 3 orbitals. 1, 2, 3. And then since it says right here, I'm going to need the d sublevel. I'm going to bring in the 4d sublevel. Now my 4d sublevel right now is empty, so I'm going to put 0 here, but 4d sublevel usually holds 5 orbitals, right? 1, 2, 3, 4. So 1, 2, 3, 4, 5. Okay. In my recipe right here, it says, wait, let me place the electrons first. I got up, down, 2 electrons, up, 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 3 electrons. The energy level goes from low to high, with 4s being lower in energy than 4p and then 4d. So 4d is the highest in energy, right? As I'm mixing or hybridizing these orbitals to make the right bonding capacity for AS, I have to use all of the S. Wait, let me use a different color here. All of the S, because it's just the one S available, 3 of the P's, and it looks like only 1 of the D's. I was going the wrong way. Let me see. It doesn't really matter what D I pick because all the D's are empty, right? So he's going to go with 1 S, all 3 of the P's, and then 1 D. I'm going to go for the first one. So I have to hybridize these, right? Mix them together, and what I end up generating is 1, 2, 3, 4, 5. 5 boxes that are degenerate. So I'm creating 5 degenerate hybrid orbitals. They're degenerate because even though I got them at different energy levels, when I mix them up, they're all going to be in the same energy level. So it has to be 1, 2, 3, 4. And they're going to be 5 boxes, right? And each of them now adopts the new mixed name, the hybridized name, sp3d, 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 sp3d. I'm running out of room, sp3d. Okay. There are 4 boxes I did not use, and these are going to be the unhybridized p orbitals. So there are 4 boxes of the of the d level I did not use. I'll leave them as 4d0 right here. They're left over just in case I need them. Okay, now I have to take my electrons that I have here from the regular orbitals and then place them in the hybrid orbitals. So I take 1, 2, 3, 4, 5 electrons. I'm going to place them here. 1, 2, 3, 4, 5. I took the electrons from the regular orbitals and I placed them in the hybrid orbitals. Now, the way I've written this right here, I have just created room for AS, or I've created an ability for AS to now bond 5 times, right? AS can now accept electrons, unpaired electrons from anything else to form 5 bonds. So of course, in the end, fluorine will come in right here. But let me see, since I did actually show you guys the valence bond model, let me show you then how this translates into the model before I bring in the fluorine. As of right now, let's see, I'll use red. So if we just stop right here, then what I'm saying is AS is now surrounded by 5 lobes. Where do the lobes come from? And this, by the way, is the valence bond model. Valence bond model. In the valence bond model, we draw the hybrid orbitals as lobes. Okay, so AS is in the middle. And then each of these hybrid orbitals now becomes a lobe that shows the bonding. Okay, so we have this here being called sp3d, and each of these lobes being called sp3d. And of course, they each currently hold 1 electron. So I have the axial position, the up and down, 1 electron. And then I have 3 that are in the equatorial position, each holding 1 electron, right? If all they're asking for is the central atom, this is what it will look like, right? So this will correspond with the image we have up here for this AS. But what we're trying to show is fluorine comes in. I'm going to use a different color for fluorine, for blue. Fluorine comes in with this 1 electron and bonds with AS. So we have room for 5 fluorines. So we fill each space with a fluorine. Fluorine comes here, fluorine comes here, fluorine comes here, fluorine comes here, fluorine comes here. And you can see this corresponds with the Lewis structure. Lewis structure shows that AS forms 5 sigma bonds, right, with fluorines. So each of these sp3ds are sigma bonds. Over here, when you're showing in the fluorine that comes in, the fluorine will come over here with figure 8 because fluorine is in the p orbital. Fluorine comes here with figure 8 because it's in the p orbital. Fluorine comes here with figure 8 because it's in the p orbital. And then where we have the overlapping of the orbitals with the unpaired electrons, that generates a sigma bond. So each of these is fluorine. So we'll call this a sigma bond between fluorine that uses the p orbital and AS that uses the sp3d orbital, okay? I didn't write it in the same format as the textbook because I don't really have their logic, but I'm just showing you that this is sigma bond right here. Fluorine uses the p orbital, figure 8, and then AS uses the sp3d orbital. And when we have the overlap, that's what's called the sigma bond. Okay? Yeah. So you have this problem here pretty much showing you, oh, that's the one that we worked on. Yeah. And you can see how they worked it out here, right? Our logic wasn't too far off from their logic, but yeah, they show you the AS in the middle and then they show you how everything works out in the bond. Once again, I just really feel like Lewis structure really anchors you when you're going through this part here. So you're not feeling lost, right?
No.
Yeah.
Yeah.
Then over here, I guess I don't have to really redraw this again. I feel like in this section here, the hybridizations past SP4, SP3, I think is very straightforward. SP3D and SP3D2, these are all very straightforward. You just find the orbitals and then you mix them up. I think the SP and the SP2 are the harder ones because you have to actually pick a P. When you're picking out of the three P's, you can pick the wrong P. Here, you're not picking the P. You're using all three P's for these three ones. So my personal opinion, these are easier. That's how you spell easier? Yeah, these are easier because you're not picking one of the three P's. You're using all three. This one here, you have to pick the right P to match it with the S, to mix it with the S. Here, you have to pick the right two P's to mix with the S. So there's a right P you can pick and the wrong ones for these ones. And that's what makes them difficult. But beyond that, I think everything else is kind of straightforward. So over here, I don't mind working this out here because you're just picking the P's the D's as they come along. In this here, it shows us mixing one S, three P's, and one D. So it shows here, you're mixing one S, three P's, one D, and then you're gonna get the hybrid orbitals, the 5 sp3 hybrid orbitals, and then you have the 4 unhybridized orbitals. So what I showed up here in the previous slide essentially illustrates this part here. Okay. And over here, you can see the same thing play out for SF6. Once you draw your Lewis structure, you have your central atom surrounded by 6 sigma bonds, and then with the fluorine. So from here, if you draw your Lewis structure, you don't always have to go through this whole step right here, hybridizing the orbitals to get to the valence bond model. You can actually skip that part. Let me show you how to do it from here, okay? Because I want to make sure I add value in the new sections. We have a central atom, right? It's S. And the central atom is surrounded by 6 electron groups. So you can have the top, the bottom. You have a single electron here, single electron here. Then you have these ones here, single electron here, here. And then here you have a single electron here. So I'm bypassing drawing the orbital diagrams. I'm bypassing all of that. The central atom, of course, based on the number of electron groups, we have 1, 2, 3, 4, 5, 6. So we're using S, P, 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 D, D. So S uses sp3d2 to form a sigma bond, right? This is bonding with fluorine. I'm going to show that to you. Let me use a different color for fluorine. The fluorine uses P to form a bond. So I'm going to draw 6 fluorines like that. So you don't necessarily have to draw the hybrid orbitals to get to this part here. You can actually skip the orbital diagrams before you get to this part. So I went straight from the Lewis structure to the valence bond model right here. Okay. Once again, fluorine uses p orbital to form a sigma bond, and then S uses sp3d2. And that corresponds with this image over here. It's a sigma bond that we're forming each time. It's the first bond, not pi. There's no bridges over here. And sulfur is using sp3d2, and each fluorine is using the p orbital to form the sigma bond. These structures here, once again, tend to be a lot more simpler. Okay. When it comes to forming the hybrid orbitals, if you're using the diagram, once again, you're going to start with 3s here, depending on what element you're actually drawing the hybridization for. You want to mix 3s orbital with all three p orbitals and then two of the 3d orbitals. Mix them up and then you get the hybridized orbitals, and each of them is going to be called sp3d2. Okay. Okay, so let me see. So for this part here, we have a table that kind of summarizes what I've been talking about so far. Remember, you want to start with your Lewis structure. So draw your Lewis structure. From the Lewis structure, count your electron groups. Remember, in electron groups, one lone pair counts as one electron group. A single bond by itself is going to be one electron group. A double bond grouped together is going to be one electron group. And a triple bond is going to be one electron group. As long as the bond or the electron pairs are grouped together, they count as one electron group. The emphasis here is, are they grouped together? And they count as one group. Okay? So if you decide you have two electron groups, the electron geometry, this is not the shape. This is just telling you how the groups are distributed, will be linear. It'll be a linear geometry. Because it's linear, remember the letters, you're going from left to right, starting with the left letter all the way to the right letter. We're going to be using the first two letters because we have two electron groups. You're going to use sp hybridization scheme. And the bond angle here is going to be 180, like we covered in the previous chapter. If you have, so here you have a central atom, and then you have two surrounding groups like that. Here you have a central atom, and then you have three surrounding groups. I'm going to use a generic atom so I don't have to commit to anything. The electron pair geometry of the groups will be trigonoplanar, three groups, and they're going to be flat. You're going to use the first three letters. That will end up being sp2 hybridization. The central atom here uses sp2 to form all sigma bonds. So either sigma bonds or lone pairs, right? The lone pair electrons are housed in the hybrid orbitals, or the sigma bond electrons, once again, are housed in the hybrid orbitals, okay? Only the pi bonds are created in the unhybridized p orbitals. So if you're dealing with a hybrid orbital, we're either dealing with sigma bonds or lone pairs, okay? So here we are assuming they're all bonds. They can be either bonds or lone pairs. With tetrahedral, you have a central atom surrounded by four groups. You have the first group on top and then the three on the bottom like that, tetrahedral. So these groups end up arranging themselves in tetrahedral geometry, hybridization, SPPP, because you have four groups, SPPP. You consolidate to get SP3. The bond angle here will be the 109.5. Don't forget the 120 for the trigonoplanar, okay? This is not new information. We're pretty much reviewing what we covered in the previous chapter. Linear, 180. Trigonoplanar, 120. Linear and trigonoplanar are both 2D. They're flat. And then tetrahedral is 3D. It is, 3D. It is not flat. That's why the bond angle here is not 90. It's going to be 109.5. If you have five groups, once again, this is going to be 3D, and six groups are also 3D. Five groups arrange themselves in trigonobipyramidal. You have the central atom, A, and then you have the five groups, right? Two are up and down axial, then you have three in the equatorial, the central. The bond angles here between the top and the side, the axial and equatorial, this would be bond angle of 90. Between two equatorials, the bond angle is 120 degrees, okay? For the side-by-side groups, and I've gone over that in the previous chapter. Okay, as far as the arrangement of the groups, that will be trigonobipyramidal in electron geometry. This is not the same thing as the shape. Look at the chart we talked about in the previous chapter to figure out what the shape should be. Hybridization, for five groups, we have SPPPD. So SP3D, right? So that will, of course, be SPPPD. So SP3D. For six groups, we have central atom A surrounded by a top and bottom group, axial group, and then equatorials. Technically, in the sixth group, we don't have equatorial or axial because all the groups are equivalent and the same. The bond angle between two bonds is going to be 90. Regardless of where you're approaching the bonds, it will always be 90. Okay, So they only have one bond angle of 90. Since you have 6 groups, you're going to use all the letters S, P, 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 D, D. And this consolidates into sp3, D2. The arrangement of the groups is going to be in octahedral fashion. Okay? And then this just walks you through the steps of what to do. Once again, start by drawing Lewis structure. Use the Vesper theory to predict the electron group geometry around each central atom. If they're asking you for molecular geometry, use the table to figure out the molecular geometry. And of course, for hybridization, remember a number of electron groups determines the hybridization. So you want to match the hybridization to the electron groups from that table, 6.1. And then you want to go ahead and sketch the atomic and hybrid orbitals, the little boxes. And then you want to show the overlap. And of course, if you're drawing the valence bond model, you want to use the bubbles for the hybrid orbitals, right? And then you want to label all the first bonds as sigma, all the second bonds using the unhybridized orbitals as pi. Remember, sigma comes from the hybrid orbitals, and then also lone pairs are in hybrid orbitals. And for pi orbitals, for pi bonds, we use unhybridized p orbitals. The ones that did not get used in the hybridization. It can be unhybridized p orbitals or pretty much unhybridized p orbitals. Okay, for the next part here, we're working on a BRF3. Okay, so for BRF3, I'm going to go ahead. I'm going to use the Lewis structure we have here just because I'm going to be a little late to my next class, but I'm going to try to finish this video right here. So we go through the Lewis structure, you draw the Lewis structure, right? And you get this one right here, BRF3. Notice we have a group here, a group here, a group here, here, and here. So technically we have 5 groups, right? Of the 5 groups, 3 are bonded groups, 2 are lone pair groups. So what they're asking for here is write a hybridization and a bonding scheme for bromine trifluoride. Okay, so what I'm going to do here, I kind of skipped over the Lewis structure part, but I want to show you guys this part here. Add a page. Okay, so for this part right here, let me see. I'm trying to see if I have... I'm trying to remember if I have my periodic table right here, because I don't really have a periodic table with me. Yeah, so bromine is right here, and it has 35 electrons, right? So you can see here, AR will be our shorthand configuration. So after AR is in brackets, then we have 4s2, 3d10, and then for bromine, it'll be 1, 2, 3, 4, 5, 4p5. So that's what I was needing. Okay. So when it comes to drawing our orbital diagram, even though we have a 3d10 here, we don't want to use this, okay? Because this is full. Remember, part of the reason for we're hybridizing is to create more bonding power. And the way we create bonding power in valence bond theory is to have a lot of unpaired electrons. The more unpaired electrons we have, the more bonding power. So let me go back here for a moment. My hybridization based on the groups I have here will be S, P, 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 D. Okay, so when I consolidate that, I'm going to be using sp3d hybridization. So I'm going to be using this S, right? I'm going to be using the P, but I also need the D. This D is not going to help us because it's not empty. Okay, so for bromine, when I actually draw the orbital diagram, I'm gonna leave the AR out. We usually leave this part out. We just want the valence sublevels. I'm gonna draw 4s2, 4p5, and even though we have a 3d10, I'm gonna pull in the 4d0. So why the 4d? The 4d is empty, and that's gonna help us to increase the bonding power. We don't want 3d because the other rationale that scientists use, 3D isn't higher energy level. I'm like, okay, but you have it in this order. For this purpose, 3D is not going to help us, so just pick the 4D0, okay? 4s only has one orbital. 4p has got three orbitals. Px, oops, my handwriting is horrible. Px, py, pz. And then 4d has got five empty orbitals here. 1, 2, 3, 4. Okay. Once again, we go from lower energy to higher energy. Remember, we pick from 4d because 4d is empty. 3d is not empty, so we're going to leave it out. Okay, let me try to fill these orbitals with electrons. I go up, down here for the 4s sublevel. And then for the 4p, I go up, up, up. 1, 2, 3, 4, 5, right? 4d is empty. Now, I've been asked this question before. Where did 4d come from? 4d has always been there. We just didn't bring it in because we didn't need it. It was empty. But for this purpose, we need 4d, so we bring in 4d. Okay? Now, our hybridization recipe says take the 1s, mix all three p's, and then pick one from the d. Okay, we can do that. We'll take the one orbital in the s, take all three in the p, and then take one from the d. Mix it up. So we end up mixing 1, 2, 3, 4, 5. We're mixing up five original orbitals, right, to make five hybrid orbitals. So let's make five hybrid orbitals here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Each has a new name. Each is now called sp3d, 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 sp3d. Woo, that was tight. Okay, now from the ones that I didn't hybridize, I don't know why the D always pulls up here. Okay, there are four up here in the 4D that I didn't use. 4D0. These are the leftovers, not used. Okay. Now let's see. I'm gonna take the electrons from the original orbitals, the unhybridized ones. 1, 2, 3, 4, 5, 6, 7. And I'm gonna place them here. 1, 2, 3, 4, 5, 6, 7. Before I do anything here, I should be able to confirm the distribution of the electrons here with the bromine. If I have this here, what I'm showing is the bromine is going to have two lone pairs. You see why I'm labeling these lone pairs? Because those hybrid orbitals are already full. If they're full, their lone pair electrons belonging to bromine alone. Is that consistent? Yes, it is. Okay. Then over here, we have room for 3 fluorines only. And that makes more sense because the fluorine will come over here, bringing its unpaired electron. Fluorine over here with its electron. Fluorine over here with its electron. And that's consistent. So the orbital diagram you're drawing has to be consistent with the Lewis structure. They have to be saying the same thing. Okay. Oh, they're showing us, I'm like, what is all of this? They're showing us what they're doing. Oh, I've already gone over this part, so I won't go over it again. Yeah. So let me from here, let me go ahead and draw, since I made it this far, let me draw the valence bond model. So the valence bond model then, based on this, right, will be bromine will be in the middle, and then bromine will be surrounded by 1, 2, 3, 4, 5. 5 hybrid lobes. Let me use the color blue so it's consistent with the picture here. Up, down, 1, 2, 3. So I have electrons in the axial position, up and down. And then I have electrons in the equatorial, up, up, up. The orbitals that are holding these electrons are called sp3d. And that's what bromine uses to form sigma bonds. Okay. Oops, I forgot. The first two are actually paired. They're lone pairs. So I'm making this a lone pair and that one a lone pair. So when fluorine comes in, the fluorine comes in right here where the unpaired electrons are. And fluorine is figure 8. So we're going to have fluorine there, and then fluorine there. Okay. Yeah. So this has to be consistent. Oh, fluorine uses the p orbital to form a sigma bond. I don't know how to designate that, but y'all know what I'm saying. To form the sigma bond. Right. Of course, they did a better job with this, but this has to be consistent with the Lewis structure up here. And that's how we built this. Of course, let's see how they show this out. Oh, yeah, right there. Okay. So you have bromine, you have the sigma bonds. Bromine uses sp3d, fluorine uses P, and that's how we get that. Okay. Oh, okay. This is when I went over it way back when. Look at the colors. For this one here, let's see. Let me just go ahead and answer this question. It says, write the hybridization and bonding scheme for, the bonding scheme for this one is going to be hard. To draw it out, the bonding scheme, I'll just point at it. Okay. So for this one here, the way this is drawn here is tricky, right? You want to actually write it out like I did over here. Okay. Let me erase what I wrote here. Oh, okay. You want to draw it out so you can actually see the bonds. So in the carbon on the left and the carbon on the right are not using the same kind of bonds or same kind of orbitals to bond because they don't have the same bonding structure, right? Their bonding is different. Let's start with the carbon on the left. The carbon on the left is surrounded by 4 bonds. So this carbon here uses, since it's 4 bonds, 4 groups, it's going to be S, P, P, P. Uses sp3 hybrid orbitals to form sigma bonds. Since it's only forming single bonds, for every single bond it forms, it uses sp3 hybrid orbitals, right? Hydrogen, on the other end, hydrogen is very uncomplicated. So let me draw it this way to indicate this is a bond. So carbon uses sp3, hydrogen here, each hydrogen here is using S. So this uses S to form sigma bond. And that's true of each hydrogen, right? Let me see if I can use a different color here. None red, none blue. What other color do we have? Purple. Okay, this carbon over here is forming a sigma bond with all the elements around it. Then it goes back and forms a second bond. Let's give it a different color. Green. This is going to be the pi bond, right? So let's figure out going back to the color purple. This carbon here, since it's using hybrid orbitals to form sigma bonds, the sigma bonds here are going to be, I see 3 groups. I have 1, 2, 3 purples, right? So carbon uses, since it's 3 groups, sp2 to form sigma bonds. Okay, it's going to be spp. To form all the first bonds, it uses sp2 hybrid orbitals. So let's see what it uses for the green bond. That's going to be the unhybridized orbital, the pi bond. Since it's the second bond, it's going to uses P, not just P, but the unhybridized, the leftover, uses unhybridized P orbital, okay, for the second bond. And then for the oxygen, we're not going to be looking at that. We're only looking at the main central atom. Does it say for everything in the molecule? But yeah, we're going to look at the central atom. So we're looking at what's happening around this carbon right here. Of course, for the S essentially uses, the hydrogen uses the S orbital, right? Yeah, this is getting very complex over here. Let me see what they show us down here because it can get very complicated. Because our focus, once again, is the central atom. Let me see what they show over here. Right, they were showing us what was happening in the central atom. You can see the carbon here using sp3 hybridization. Each hydrogen here using the S orbital. You can see the oxygen here, which I didn't really do much with the oxygen. The oxygen uses the regular p orbitals to form its bonds. It uses the p orbital for the first, px orbital for the first bond. Then it goes back and uses the p orbital for the second bond. So we're not dealing with the oxygen so much. Our focus, once again, is the central atom. But this is a regular p orbital. And then this one here is an unhybridized p from the carbon. Okay? The biggest thing here is you guys recognizing what the labels are. For this oxygen, this is a regular p orbital. How do I know it's p? It's not a different color. It's not hybridized. And this one right here will be probably p, another p orbital. That's up and down. So that it might be a pz. This is like a px and this is a pz. They didn't ask you for all that. They just said p and then p. But the carbon uses an unhybridized p orbitals for the second bond. Okay? And I gave you guys an example here. I'm trying to retrace my steps based on what I covered before. That for this question here, they're asking you to write the hybridization and the bonding scheme. The biggest thing I want you guys to know in a molecule like this for HCN, you want to draw the Lewis structure, right? When you draw the Lewis structure, it works out to where carbon forms a single bond with hydrogen, but it forms 3 bonds with nitrogen. So the first bonds formed are going to be sigma. All first bonds will be sigma. The second and the third bonds will both be pi. And for the sigma bond, carbon uses sp hybridization. For pi bond, it uses the unhybridized bonds, or orbitals. Unhybridized p orbitals. Okay? So once again, sigma bonds and lone pairs, you have to use hybrid orbitals if it's a central atom. And then for the double bonds, the second and third bond, it has to be unhybridized p orbitals. Okay? I feel like I sound like a broken record. Once again, with this one here, to see all the bonds that are being used and formed here, you have to draw out the Lewis structure. So let me erase the labels I have here so we can go through. Once again, I'm going to show you all the sigma bonds from the carbon. So these are all the first bonds from the carbon, right? That's the first bond, that's the first bonds here. Oh, interesting. Let me use a different color here so it's not as repetitive. These are all the first bonds in this carbon here. Then this would be the second bonds. The second bonds right here. Okay? Okay. For the carbon on the left, the first bond is going to be, these are all sigma bonds. Since we have 3 groups, a group here, and a group here, the sigma bonds are going to be done with sp2 hybridized orbitals, right? Because we have 3 groups, so sp2. On the one on the right, the carbon on the right, same thing. Because we have 3 groups, the sigma bond will be done with sp2 hybridized orbitals, okay? The second bond, the additional bond will, of course, be, oops, this is not showing properly. The additional bond will be unhybridized p orbital. This is going to be the pi bond. Again, it will be unhybridized. And when you go through the lesson again, you see a trend here. Unhybridized p orbital. The one that bridges over, right? For each hydrogen here, they use S, 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 S. Hydrogen is always very simple and very straightforward. It comes in here and just uses S each time. Right. So once you draw all this out, you see how it plays out. And they show it to you right here where you're drawing stuff from. Once again, in the picture form, you can see this is the first bond ever formed between the 2 elements. That would be a sigma. So this is a sigma bond right here. You can see that. This is the first bond ever formed between these 2, also a sigma. First bond formed here, also sigma. The carbon each time uses sp2 hybridized orbital to form all sigma bonds. Same thing with this carbon over here. There's 3 electron groups around it, so it uses sp2 hybridized orbitals to form all first bonds. The additional bond that's formed is the pi bond, and that has to be the unhybridized p orbital right here to form the pi bonds. Oh, I got to the end. That's the end for this video. Okay, so this officially marks the end of chapter 6, part 2. Okay, so I'm going to go through and try to encode the video and then take out some extra stuff and then just post it. Okay.